join together to make molecules. And I want to stick with now, instead of ionic compounds, I want to keep talking about covalent compounds. Covalent compounds, where atoms are stuck together and electrons are being shared between all the atoms that are stuck together. Electrons are being shared, not necessarily equally. So here's the deal. Oh, I know we talked about bond orbitals, didn't we? Yeah, we talked about how atomic orbitals overlap. Couple electrons are there to make those bond orbitals. Well, I'm going to kind of build on that. There's this thing called the valence shell, and we know what valence electrons are, right? Valence shell electrons. And the repulsion, I'm going to try to kind of walk you through this. Valence shell electron pair repulsion theory. And it just actually gives us the geometry around an atom. So we talked about the two types of bonds. I'll kind of remind us what this looks like. We could have a carbon single bond to a carbon double bonded to a carbon, or a pair of carbons that are triply bonded. Okay, this is a sigma bond, this is a sigma and pi, this is one sigma and actually 2 pi bonds. So we have this kind of differences in covalent bonds. The sigma bond is the primary bond, and the pi bond is what we call the secondary bond. What they have in common is that they have 2 electrons that create those. Those are different covalent bonds, kind of like call them vanilla and chocolate. The other thing is that we talked about this the other day, that those 2 electrons that make that sigma or pi bond spatially are in different places. So as I've drawn it up on the board, this would be carbon single bond carbon. So that gray is a sigma bond. This is carbon double bond carbon, just the black. And the white is actually hydrogen, is also connected to the carbons. But where the gray there is the sigma bond and the pink purple represent the pi bond. And then this would be carbon triple bond carbon, where we have the sigma bond and pi and pi. So just to kind of remember how that goes. So the sigma bonds and the lone pair electrons are going to repulse or orient themselves away from the atom as far as they can. Thus the repulsion part in the valence shell electron pair repulsion theory. So that kind of gives us kind of what we say geometry or shape around an atom. Not shape for the molecule, but at least shape around an atom. So like I showed you, the sigma bond actually lies between the nuclei. Okay. Now the pi bonds are kind of outside the sigma bond. Once you have the primary, you can have secondary. Once you have sigma, you can have pi, the reserved. So when we're talking about structural geometry or electron pair geometry, we're focusing on the sigma bonds only, not the pi bonds. Sigma bonds and actually lone pair electrons gives what we say electron pair geometry around an atom. Okay. So if you're familiar in biology, if you want to grow a pea plant that has certain characteristics, you can blend 2 and make a third one. Okay, that process is what we call hybridization. So a similar thing happens with regard to an atom. We have atom A and atom B, and they're going to be joined together. They have to reach out. We talked about atomic orbitals to go ahead and overlap those atomic orbitals to make the bond orbital between them that connects them. Well, we have this hybridization process that then actually, after an atom hybridizes 2 or 3 or 4 or 5 or 6 or 7 or 8 of its atomic orbitals, it spits out those hybridized orbitals that can participate in either lone pairs or sigma bonds. Notice what they can't participate in are pi bonds, hybridized orbitals, only sigma bonds and lone pair electrons. So I'm going to talk you through this process of describing the geometry around an atom within a molecule, not the molecule itself. So electron pair groups could either be we have a few possibilities. Electron pair group could be dot dot or lone pairs, lone pair. It could be a single bond. Okay, a double bond would be a group. A triple bond would be another group. Okay, and these groups will repulse from them apart from each other as much as possible to give shape or geometry around an atom. What happened to my builds? Not finding it under my builds. So I want to focus on 3 different scenarios, 3 different hybridizations, okay, of atomic orbitals that give you these different numbers of groups, electron pair groups. We'll give you 2 groups. You're going to get a linear shape. I'll show you what that looks like. Again, it's all about repulsion. So if 2 groups are going to repulse as far apart from each other as possible, then it's going to be in a straight line. I had somebody paint these recently. That's so pretty. She did a great job. Okay, so all that means is you have 2 electron pair groups. They could be lone pair electrons, single bond, double bond, or triple bond, and they go as far apart as possible. Okay. Then the next one is we have 3 things that are spreading apart from an atom as much as possible. And actually, I've got one more up here. Got some atoms in there. So if they spread as far as possible, actually, we're going to call this shape trigonal planar. And then the last one I want to talk about and hold you accountable is if you have 4 things that spread apart from each other. And it's going to look like this. And we call this tetrahedral. Okay, so linear, 2, trigonal planar, 3, tetrahedral, 4. That's it. And again, what I'm talking about is the geometry around this orange atom, the geometry around this brown atom, the geometry around this black atom. But keep in mind, and this kind of throws us off sometimes, instead of joined to an atom, actually this could also, or instead, be lone pair electrons. Take a look. So, if you have 2 things right here, actually, oh my God, that's funny. The bond angle would be 180. The bond angle here is 1/3 of 360, which is 120. And this bond angle right here in tetrahedral is 109.5. So the last column actually kind of is reminiscent of what are the electrons, where can electrons reside, electron configurations. We talk about S-type orbitals, P-type orbitals, D and F. So that's actually what that's referring to. In this case, this orange atom has taken one of its S and one of its P. They have put them together and hybridized, spit out 2 hybridized, equal hybridized SP orbitals. This one, SP2. This brown atom's taken one of its S and 2 of its P's, like magic, and spit back 3 equal hybridized orbitals. Black atom is SP3, 1 S and 3 P's. Gives 4. And the cool thing is these are all, you can't tell, and I think I might have a slide coming in, you can't tell which is which. There are 4 equal hybridized orbitals. So, are all my bills that way? Oh my gosh. Okay. So this is kind of a busy slide. If we look at the first row is only talking about 2 electron groups. They're both bonded to something. That would be this. They're lone pair electrons. Bond angle 180. This is molecular geometry, which is different than electron pair geometry. It coincides now just because it does, but the electron pair geometry is linear, as is the molecule. My builds are backwards. This guy, well, let's go with the 4 one. This guy down here, then we have a set of 4 rows here. And each of them have 4 electron pair domains spreading from them, 4. So you're back to tetrahedral, this sort of deal. You have some options here. In this first case, we actually have, it's bonded to 4 different atoms, which is kind of what I'm showing here. Tetrahedral 109.5, here's an example. This next one right here, one of these actually is a lone pair electron. So I show that by just kind of doing this. It's still tetrahedral. I have 4 electron pair domains coming or emanating from that black atom, but one of them, one electron domain actually is where that pair of lone pair electrons are. So we say the shape is still tetrahedral, bond angle 109.5. An example of that is actually ammonia, NH3. So this actually, lone pair electron helps give shape to this kind of pyramidal molecule. And then the last scenario, it's kind of weird. Oh yeah, water does this. Water actually does this where it's still sp3 orbital hybridized, tetrahedral electron pair geometry, or tetrahedral is the electron pair geometry around the oxygen atom. We have oxygen, hydrogen, hydrogen, lone pair electron, lone pair electron. Okay, so we say that the electron pair geometry is tetrahedral around the oxygen atom, but the molecule itself, you probably see up there, is bent. And I don't focus on molecular shape as much as the electron pair geometry around an atom, which includes the lone pair electrons. Okay. Just make sure we're all on the same page. This is something we covered, I think, the other day. But if I was going to draw the Lewis structure of a water molecule, it would look like this. Oxygen, hydrogen, hydrogen. These are sigma bonds. Lone pair electron, lone pair electrons. So that's kind of what we have going on. And this will be reinforced in the lab we're going to do on next Tuesday. The one that I'm revealed right here, we have 2 rows that represent actually where 3 electron pair domains are spreading apart from a central atom. A couple of options there. The first option says it's connected to 3 different atoms, no lone pair electrons. It's trigonal planar, bond angle 120. The second option is where you take one of these. So it's got sigma bond, or it's got electron domain with a real atom here, and this is lone pair electron. Again, even if it's 2 electrons, a pair of lone pair electrons up here, it gives geometry to the atom, and actually it will give geometry or shape to the molecule as well. Okay. So this is just similar to what I talked about. I feel like I have a lot of slides that do the same thing, trying to show you that shape around an atom. So this is sp orbital hybridized, okay, orbital hybridization. This is sp3 orbital hybridization. And this is sp2, orbital hybridization. It's called the conservation of orbitals, where, do you see where, for instance, sp, if I take 1 s plus 1 p, I get 2. Here, this is sp2. If I take 1 s plus 2 p's, I get 3. And that's exactly how many hybridized orbitals are created during the hybridization process. This sp3, I take 1 s and 3 p's, 1 plus 3 is 4. And that's exactly the number of hybridized orbitals I see come out of that hybridization process. So we call it sp3 hybridized, creates 4 hybridized orbitals. Okay. Oh my goodness, they're all backwards. Balloons work well to kind of show you the repulsion part. So I'll just put them all up here. The first 3 are ones that we talked about. Going from left to right, you see the sp orbital hybridization, 2 things, gives you that linear shape. The next one, sp2 orbital hybridization, gives you 3 things, and we have that trigonal planar. I think of my, it's on, I don't have my pen, that's okay. I'll put it up here on the board. The next one I'm going to hold you accountable for, sp3 orbital hybridization, gives you a tetrahedral shape. kind of it where these balloons are pulled together. Think of that as the atom that's creating these hybridized orbitals. The next two I'm not necessarily going to hold you accountable for, but they are definitely there. The fourth one, excuse me, where you see, actually that is sp3d orbital hybridized, and you can see the name of the structure is trigonoplanar. And you can see that in this situation, the atom that's going to spit out the hybridized orbitals has taken one of its s, 3 of its p's, and 1 of its d's. So if you add those all up, you're going to see that actually you have 5 things that are emanating from that atom, 5 hybridized orbitals. And the last one is sp3d2, and it is, I'll show you that, octahedral? Yep. Octahedral. And again, due to the conservation of orbitals, we have 1 plus 3 plus 2. You must have 6 things, and that's as far apart as they can get from each other around that atom, those electron pair domains. Again, like I said, I've got a lot of slides that say the same thing. From left to right, you have sp, sp2, sp3, sp3d, and sp3d2. And just these are electron pair geometries around an atom that is creating these hybridized orbitals. And what can occupy those hybridized orbitals are only lone pair electrons and sigma bonds. That's it. Goodness gracious. Yep. I have like very many slides. Okay, so ammonia, I feel like we looked at ammonia the other day. We could write the Lewis structure of ammonia, and this is what it looks like. When we do the lab next Tuesday, I will definitely make sure that you have, I'll just kind of recreate it here. You have this table handy where the first column, and a few slides ago, it says number of sigma and lone pair electrons. And it goes 2, 3, 4, okay? And then the next column says, or I don't know if this is in order, but I'll put it this way. It's not in order, but hybridization. Okay, so if you have 2 sigma bonds and lone pair electrons, that must be an sp orbital hybridized, and it gives you your linear shape. If you have 3, it must be sp2 and trigonoplanar. And if you have 4, you must be talking sp3, and it's tetrahedral. And we have this bond angle. So this is 180. We've done this a few times. 120 and 109.5. That's all kind of what we've been talking about. I mentioned that because on a Lewis structure like this, we should be able to go ahead and use that information to kind of draw some conclusions. So the way you use this table is this. I can ask the electron pair geometry around the nitrogen atom. And in order to understand that, you would put your focus on the nitrogen atom and you would count sigma bonds, which I got 3, and lone pair electrons, which I got 1. 3 plus 1 is 4. And that's where on a table like this, I would say, oh, I got 4. And I'd be like, oh, I know all that there is to know, basically, about the geometry and the hybridization around the nitrogen atom. So, did you guys have these answers yet? You guys have these? Okay. So it's sp3 orbital hybridized, structure geometry, tetrahedral, bond angle 109.5. Oh, you didn't have these, but you did have these. Notice that this little quick squiggly thing means approximate. So I'm going to actually have a slide coming up to show you why it's approximate and not exact. Okay, so let's do another one. Okay, formaldehyde, and again, we talked about Lewis structures before, you guys will be drawing them in lab, but we're assuming that the positive valence electrons brought by these 4 atoms are distributed properly here, and we have complete octets. I'm liking it, looks good. Hydrogen has a duet. But let's see. So what do you guys have for you?
Testing.
Okay, thanks. So around that carbon atom, you can see that I count, now double bonds is 1 sigma, 1 pi. So I only have 1 sigma bond here in this double bond, and of course I have a sigma bond to that hydrogen, to sigma bond to that hydrogen, no lone pair electrons. So, Gabe, what would be the orbital hybridization?
SP2.
It would be SP2. I'm liking it. So, RJ, what would be the electron pair or geometry? Yeah, trigonal planar. Very good. And what would be the bond angle? 120. That's it. You guys got it. That's perfect. So a lot of times what I'll do for this exam is you'll make simple little structures. Again, we're gonna kind of hit that in line on Tuesday. But the other thing is you'll interpret a little structure. So you'll tell me electron pair geometry around that. Yes, sir. Yes, sir.
So I'm a little confused where the SP2 comes from.
So, well, you remember like the 1s2, 2, yeah, okay. So it just says that an atom is taking one of its atomic orbitals, that's an s type, and 2 of its, so it's sp2, so 1s and 2 p's, and basically taking its atomic orbitals and taking those 3 and then reaching out 3 equal hybridized orbitals. They're each what we call sp2 hybridized orbitals. So it's atomic orbitals reaching out to participate in the single bonds of the electrons. This actually is what you guys just told me. It's the same structure. Okay. So do you see why here it's saying we're going to focus on the chlorine atom, and we count 1 sigma bond and 3 lone pair electrons. Okay. So we'll start with RJ. So what would be the orbital hybridization? It would be sp3. Very good. So Cole, what would be the structural geometry? It's sp3. It is tetrahedral. And I don't have anything for you, Gabe, because the bond angle doesn't really make sense. There's not really, to be a bond angle, you need to have something that has 2 bonds, an atom, and then 2 bonds going out to other atoms. So, but electron pair domains would be kind of spatially separated at that 109.5. Cool. So, either one of these carbons, it's symmetrical. Again, what we, like at the top of this column, it says count sigma bonds and lone pair electrons. So, don't forget, a double bond is just 1 sigma bond. So I got sigma, sigma, sigma. So I got 3 sigma bonds, no lone pair electrons. So maybe back to you, Gabe, what sort of orbital hybridization would it be? sp2, very good. Yeah, sp2. Yep, and then what about the bond, what about the, thank you, structural geometry, RJ? Trigonal planar, yep, the bond angle, cool. 120, you guys got it. See, they're really, as long as you make sure we're all on the same page, we're just pointing to an atom. Now, I spend more time talking about the geometry around an atom. It's called electron pair geometry. Then you're a hop, jump, and a skip away from taking all of the little individual geometries and making the big geometry of what we call the molecular geometry. Don't spend as much time on that. Okay, so yep, pick either carbon, and you're looking, remember triple bond is 1 sigma 2 pi. So we have one sigma there, one sigma there, so you're looking at 2. So what do you think, Cole? What would be its orbital hybridization?
Just SP.
Just SP, yep. And so structural geometry, Gabe?
Linear.
Yep. Bond angle, are there? You got it. And this idea about the shape of a molecule is a player in a lot of things, how it will behave, a lot of medicines, a lot of just chemical reactions count on it being a certain shape. So if we look at all 4 of these compounds, you would tell me that around the carbon atom, I've got 4 sigma bonds. So you're looking at sp3 orbital hybridized tetrahedral. Around the nitrogen atom, I've got 3 sigma bonds, 1 lone pair electron, so I got 4 things. So again, tetrahedral. Around the oxygen atom for water, I've got 2 sigma bonds, 2 lone pair electrons, so I've got 4, okay? So each of these actually is the central atom's sp3 orbital hybridized, so you would expect electron pair geometry to be tetrahedral, so we say there should be a bond angle of 109.5. But here's, and if I ask you on a test, that's what you'll tell me what the bond angle is. But here's where I need to say it's not, that's not exactly right with regard to the bond angle. What happens, and here's each one of these. So again, the central carbon atom, the central nitrogen atom, the central oxygen atom. In all of these cases, we're looking at sp3 orbital hybridization. But think of these electron pairs as being kind of a little more fluffy, a little more repulsive than just being bonded to something. So what happens here then is we're going to see this bond angle here between, for NH3, it's actually a smaller angle than this bond angle. And here where we have 2 electron pair domains that are occupied by lone pair electrons, this is even fluffier. So this is going to be the smallest angle of them all. So here's CH4, a classic case of a 109.5 tetrahedral. As long as these are equal, that's what's going to be the case. Here's ammonia, and I'm not sure the bond angles, but I've got it on the slide coming up where you can see this is even less, okay? And actually this is the least of all 3 of them, less than 109.5. So 109.5 in methane, that's great. You add 1 lone pair electron around the central nitrogen atom, you're looking at 107. You add 2 lone pair electrons around the oxygen atom, and you're looking at 105. But again, on a test or homework, you could please tell me that this 109.5. All right. So we're going to go kind of we're going to go counterclockwise, starting with this carbon atom. I'm going to ask you directed questions, hopefully in kind of the same order. So starting with you, Gabe. So this carbon atom, how many sigma bonds?
4.
4, perfect. How many lone pair electrons?
0.
0. And I'll just kind of pick on the same person for all the questions. All right, you're doing great. So what sort of structural geometry do we have? Yes, exactly. Tetrahedral. Perfect. That's tetrahedral. So, RJ, I'm picking on this nitrogen atom. Again, these are questions not about the entire molecule, about a specific atom. So, that nitrogen atom, how many sigma bonds?
1.
1. Perfect. How many pairs of lone pair electrons? Just 1 pair. Perfect. So, what sort of structural geometry would you think around the nitrogen atom?
Linear.
I'm liking linear. Yep. You got it. So Cole, we're coming around to this carbon right here. So how many sigma bonds?
I don't think I was here for this part.
Okay.
The 2 lines, do they count as just 1?
Exactly. The 2 lines count as 1 sigma, and the other one's what we call secondary bond or pi bond.
Okay.
So, yep.
Yeah, the trigonal planar.
Yep. So there's 3 sigma bonds, no lone pair electrons. And so you're looking at 3 and trigonal planar. Yep, very good. So back to you, Gabe. So this oxygen atom, how many sigma bonds?
One,
One, very good. How many pairs of lone pair electrons?
two,
Two. So what sort of geometry would you expect?
trigonal
Trigonal planar, perfect. You got it. Very good. And then one more slide. And I'm going to ask some questions about bond angles. But to me, I need to know the geometry before I can knock out bond angles. So I'll tell you, RJ. All right. So I think I'm just going to go for it. What would the bond angle, I feel like we maybe talked about this carbon. What would the bond angle here be?
109.5.
109.5. And he got that from saying, well, it's got four things scattered around it. So those would be sigma bonds and lone pair electrons. So it's tetrahedral, so the bond angle is 109.5. And we didn't do this atom, so I'm going to ask this in a series of questions, Cole. So this carbon atom right here, so how many sigma bonds around this carbon atom?
3.
Very good, perfect. And no lone pair electrons. So what is the shape?
Trigonal planar.
Perfect. And then what's the bond angle?
120.
120. Yep, exactly. And I am one of these that I kind of think through it in stepwise to get to those answers. So back to you, Gabe. So I'm picking on, I want this bond angle around this particular carbon atom, but let's go at it piecewise. So how many sigma bonds extending from that carbon atom?
2.
2, perfect, and no lone pair electrons. So what do you think about the bond angle?
Maybe 1 year, something
Linear 180, yep. So this is where, again, you just identify what it is with regard to sigma lone pair electrons, and then you know everything you need to, you might be asked about that particular orbital hybridization. Yep, 180. 180, Grady. So yeah, this actually goes to you. This is correct for the semester. This assignment will be due next Wednesday. I say it's due next Wednesday, but we'll have to see if I feel like it's something. We'll see if I remind you. The reason next Wednesday is because I don't want you to have to do this until we do the lab. My Chrome has been possessed. It's been hijacked. I don't know what to do about it. Terrible. But anyway, that was my Chrome interjecting. So I don't know if this was confusing, but so there's nothing due. Okay, this is I'm holding this back because I want to talk about. I wanted to do the Tuesday lab before I do that. So on Friday we have a little bit to finish up with Lewis structures. I want to talk about resonance structures, which is important. So you want to get notes. I think RJ won't be here that day. And then I'll talk about the difference between pi and sigma, which should help you, Gabes, if you're cold to hear about the two types, sigma, pi. And then Monday, bring your calculators if you want to, but you don't have to. But Monday, we're going to begin doing a little bit of calculator stuff with this unit. Okay? Awesome. See you Friday.